Hello and welcome. Today we'll be going through the OptiAssist for Abaqus. This is tutorial 3, the ply shape optimization of a front wing using an advanced response. This tutorial aims to use multiple methods, one of them being the ability to define multiple ply pattern sets, each one having its own different coordinate system. Another is using a laminate thickness constraints with predefined element sets. And another would be the ability to define an equation-based function, considering multiple displacement responses. As you can see here, I've already loaded up the initial model in the post-processor, in this case Abaqus, where we have an initial displacement of 87 mil. The overall optimization will be to aim for lowering this displacement to around 34 mil, so over half. To begin, if we go over to OptiAssist for Abaqus and click on Load Abaqus Input File and click on Tutorial 3. Once this is loaded in, the first thing we are going to do is define a new thickness set data. So under thickness set data, we'll click new, and under description, we'll be calling this one cloth, with a minimum plies being 1 and the max being 10. We'll click OK, and we'll repeat this process for the unidirectional, or UD for short. Min plies 0, max plies 20. We'll click OK, and under the ply summary table we are going to select all the plies with the ply and then a number by holding down Shift and clicking at the bottom there, and then clicking hide. From there we sort the plies by their material. We can highlight all of the UD fiber plies, as well as clicking on the UD thickness set data and clicking Assign Thickness Set, and repeating that process for the cloth fiber. Once you have done that, we go over to Ply Pattern Subdivision Data and click on New. The first set, we'll go over to the description and name this first set Center. With the symmetry coordinate system TOPM 1, with a length of x to be 30 by 30 by 500. We'll click OK and repeat this process. This time for main wing, the system now being TOPM 2, and this will also be 30 by 30 by 500. We'll click OK, and then by referencing the plies by their position, we'll click on all the center or CTR plies, as well as the subdivision data and clicking Assign Subdivision, and then again for the main wing. Once you have done that, we can click Next. No ply linking is required for this optimization, so again we'll click Next. The goal for this optimization is the default minimized mass, so again click Next. For the constraints, we will be creating multiple, so for the first one we'll click New, and under the type, make this one displacement, under the name forward displacement, or FWD underscore disp. For the step, we'll set it to be 1 FW load with a lower bound of minus 10 mil. For the selection type, we'll change from the drop-down node to node set, and then select forward displacement, or FWD disp. The component for this will be in Z. Once you've done that, we'll click Create, and then repeat the process for the other displacement. Once you have done that, we will create a third constraint. This time it will be the composite thickness. So click on New, under the type, composite thickness. I will name this one thick all, or THK underscore all. Low step will be all, and the upper bound will be 10. Under the selection type, we'll change it to LSET, and then at the bottom, all designed. Click Create. And for the fourth one, we'll click New, thick rear edge. For the final advanced constraint, we'll again click New, and under the type this time we'll go Advanced, calling this one Rel Disp, load step all, type Advanced, upper bound of -1, and then click Add New Response. Automatically it will be set to R5. This time for the R5 it will be for the rear load in the Z direction for the node set of rear displacement. We will then repeat this process for R6, which will be for the forward load. Under the response equation, we will type in R5 minus R6, the newly made response IDs. We'll click. Once you've done that, we'll click Next, and once you're happy with the solution type setup, we'll click Submit, and the optimization will begin to run.
Once the optimization has finished running, if we go back to your Abaqus CAE and load up the new optimized model, you'll be able to take a look at it and its new laminate thicknesses. You can also take a look at the thicknesses of the plies individually to show which of the plies have been considered in the optimization. This concludes the tutorial.